everybody, this is Miss Bufford, and in this video we're going to talk about mixtures versus pure substances, and we're also going to discuss some separation techniques. So your learning goals for this building block are to be able to discuss lab techniques used to determine if a substance is a pure substance or a mixture, and just to be able to determine if a substance is a pure substance or a mixture. All right, so the first thing we're going to talk about are pure substances, and the first type of pure substance we're going to discuss are pure elements. So pure elements contain only one type of atom, or atoms of a single element from the periodic table, and so that is our first example right here. That's what I'm talking about, just single atoms of elements from the periodic table. And then the second type of pure element would be atoms that can't exist alone in nature, so they pair up with a buddy that is the same kind of atom that they are. So and the reason this happens is because these elements are so reactive that they just can't be alone. And if we have a pure sample of that substance, then all we have are atoms of that element, and so they tend to pair up and form little molecules of that element. And so we call these polyatomic elements, and they include more specifically a group of elements that pair up in groups of two. So these are called diatomic elements. And you're going to need to be somewhat familiar with these, because if they show up in a chemical equation later, you're going to have to know that this 2 needs to go behind them when they're all by themselves. So hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, and astatine are all diatomic elements, meaning they exist in pairs of 2. And then we have other polyatomic elements that include phosphorus and sulfur. All right. The other type of pure substance that we're going to talk about are pure compounds. So a compound is a molecule or a substance that has at least 2 or more types of atoms that are chemically bonded together. And if it's forming a molecule, so this example up here with this box has molecules, and you'll see that each one of these little molecules has 1 purple atom and 3 green atoms. And all of the molecules are identical, and so they're sharing the same chemical and physical properties. And so that's really important when we're talking about pure compounds. All of the atoms, molecules in that substance have to be identical, and if they are, then they'll all have the same chemical and physical properties. But there are other compounds that don't necessarily form really small molecules. They clump together and they form these repeating patterns of atoms, or rather ions, and they form crystals. And so they just continue to build on in that repeating pattern until they build these crystals that are large enough for us to see. And the idea here is that they're still forming a substance that has the same consistent chemical and physical properties throughout that crystal. So it's still the same substance. All right, so some examples of pure substances would be, pure elements would be anything from the periodic table. If you had a pure sample of any element from the periodic table, that is a pure element. So I just have a few here. So I have iodine. There's some iodine vapors, really pretty. Sodium, metal, and then carbon, which can actually exist in both the graphite and the diamond form. So that's the only difference here between these two. They have the same chemical formula, but some of them, in order to form a diamond, graphite has to be exposed to extreme heat and pressure to squeeze it down into that shiny diamond that we know. All right, and then pure compounds. Some examples would be sodium chloride. So this is table salt, the stuff that you put on your food, and it is sodium and chlorine combined into one substance, and that forms those little crystals of salt, sodium chloride. Water is hydrogen and oxygen, so 2 hydrogen atoms and 1 oxygen atom that come together to form individual water molecules. Right, so they look like this. And then we've got sugar that forms individual molecules of sugar, but these are really big molecules. As you can see, there are 12 carbons, 22 hydrogens, and 11 oxygens in this sugar. And they do form crystals. but they are not the same type of crystals that we would find in salt. And we'll learn about the differences later. You don't have to worry too much about that right now. But just know that, there's 3 elements in that formula right there. So that's definitely a compound. And then this one right here, we've got copper and chlorine. So this is copper 2 chloride, and it is a compound as well, forms crystals. All right, so now let's talk about mixtures. Mixtures can contain more than one type of particle that are not chemically bonded. So the important word there, the key word, is that in a mixture, we have things mixed together that are not reacting with each other. They're not forming chemical bonds. So we could have an element-element mixture like this right here, or like this. We've got single atom elements here. We've got diatomic elements, molecules here. And then we've also got a mixture of diatomic elements right there. So all 3 of these first boxes represents different mixtures of elements. So element-element mixtures. Then we can have element-compound mixtures. So if we take a look at this one over here, we've got a diatomic element right there, and then we've got a, we'll say it looks like water with 1 oxygen and 2 hydrogens. That's a compound right there. So maybe that's a mixture of oxygen and water. So that would be a compound element mixture. And then we could have a compound-compound mixture. And I don't have a picture to show you this, but let's say we had water, H2O, and it was mixed with carbon dioxide. And so that would be a compound-compound mixture if we had those 2 elements mixed together in the same container. Okay, and then mixtures can be broken down into either homogeneous mixtures or heterogeneous mixtures, and we'll talk about those on the next couple slides. All right, so homogeneous mixtures is a type of mixture where the components, they're not clearly visible. So you can't look at it and easily discern the different parts of these mixtures. These are blended so well that they just look like one substance. An example of homogeneous mixtures would be solutions. And although we tend to use the word solution to describe more liquid mixtures, the word solution actually can describe any mixture that is where the components are in the same single state. So some examples of solutions would be salt water. So if we took salt and we dissolved it in water, we have now formed a saltwater solution. And if we look at that, after all the salt has been dissolved, we can't see the salt anymore. All right, so that is homogeneous. And then sugar, once all that sugar dissolves, we get the same thing. We get a homogeneous mixture where it looks like water if you didn't know any better. And then brass metal would be an example of a solid solution. And when we mix metals, we also use the term alloy. But brass is a solution of copper and zinc mixed together. And then the air that we breathe can be considered a solution. There's lots of different gases in the air we breathe. We've got nitrogen, we've got oxygen, we've got carbon dioxide and argon, along with all the other stuff that gets put into our air. So that could be considered a solution, and it's homogeneous because we can't see all the different gases in there. All right, and then another type of homogeneous mixture would be colloids, and these are mixtures where the particles are suspended in another substance and they don't settle out. But these particles tend to be really, really large, either really large molecules or particles that are so small that they're just not heavy enough to settle out of that solution. And so some examples would be Jello or gels would be an example, or even lotions, which are emulsions. So emulsions have the oil component and the liquid water component, but the oils have been broken up into such tiny pieces that they actually stay suspended in that watery solution. And that's why you can spread them on your skin really easy. And then we have heterogeneous mixtures. So in this type of compound, the components are clearly visible and can easily be discerned from the rest of the mixture. So some examples would be like Chex Mix. You can see all the different pieces of snack in your Chex Mix. Soil, you can see the different components of soil if you take a close look at it. Chocolate chip cookies, or cement. If you look really close at cement, you can see all the rocks and the sand and stuff mixed in there. Another type of heterogeneous mixture, or a type of heterogeneous mixture, would be a suspension. And suspensions are mixtures where the particles are sufficiently large that they will eventually settle out. So you could mix them up and get them to temporarily form, what we call a suspension, but then eventually those particles are heavy enough that they're just going to settle right out of that solution. They'll go to the bottom. So chocolate milk is an example of this. If you've ever used the powdery chocolate milk to make yourself a glass of chocolate milk, then when you get to the end, if you haven't been swirling your cup the whole time, you notice there's a little bit of chocolate powder still at the bottom of your cup that's settled out. And then vinaigrette dressing. So when you use that oil and vinegar dressing, you shake it really hard to get it all to mix together. And then you pour it on your dressing. But then once you let it sit on the table for a while, you'll notice that the oil and vinegar will start to separate again. And then unhomogenized milk, or milk that is fresh from a cow, will separate into cream and water. And what they do these days with milk is they put it through a process called homogenization. And so we no longer have to shake our milk before we put it into our cereal or use it or drink it in order to get the milk fat portion to remix with the watery portion of the milk. Homogenization occurs when they take the milk and they force it through teeny tiny openings with high pressure. And what that does is it breaks those milk fat particles into a lot smaller, teeny tiny pieces that then can stay suspended in that liquid. And so what we're doing when we homogenize milk is we're taking it from a heterogeneous suspension and we're breaking up those particles. And so they're small enough to form a homogeneous colloid. And then that's why we don't have to shake our milk anymore. All right, so this is just an overview of all the stuff that we just talked about. It just kind of shows you the relationships between everything. This would be a good idea, just to kind of know the relationships between pure substances and mixtures and the different types of pure substances and mixtures. All right, so now let's talk about separation. And first, we're going to talk about the differences between separating mixtures and separating pure substances. So when we're dealing with mixtures, these can be separated using the physical properties of the components of the mixture. And really what we're doing here is we're just taking advantage of the differences in those physical properties. So if we have something that has one physical property that sets it apart from the rest of the stuff in the mixture, we can maybe take advantage of that property and use it to pull something out of that mixture. So an example of this would be salt water. So if we had salt water and we needed to obtain a sample of salt from that water, let's say we were at the ocean and we wanted to purify some salt, then we could put some salt water in a little evaporating dish and heat it up, and the water would evaporate out and it would leave behind the solid dissolved salts that were in that water. And this happens because the boiling point of water is a lot lower than the boiling point for sodium chloride or for salts. And so that's one way we could take advantage of the differences in some physical properties. And then when we're talking about separating pure substances, these can only be separated using either a chemical process. So compounds, we will use a chemical process to break down into the component parts. Or if we're talking about elements can't be broken down using chemical processes. They have to be broken down using nuclear processes or nuclear processes. All right, so nuclear processes have to break down elements into, the parts, the things that make them up, whatever their atoms are made of. And chemical processes are used to break compounds down into the atoms or the individual atoms that make them up. All right, so we're not going to talk a whole lot about separating pure substances in this video. We're going to focus on techniques that we can use to separate mixtures. So the first technique that we're going to talk about is distillation. And distillation separates liquids based on boiling points. So these substances are heated, and those substances that are in that mixture that have a lower boiling point are going to start to evaporate first. Once that temperature for that boiling point is reached for that first substance, then that substance will begin to evaporate out of that mixture. And then once all of that substance has left the mixture, then the next boiling point, then the next one with the next lowest boiling point will start to evaporate out of that mixture. And so if we take a look here at this example of simple distillation, simple distillation is used when the substances you're trying to separate have a pretty big difference in boiling point. So it's pretty clear cut where the end point of your distillation will be. So you get one thing to evaporate off, and then, we have a while before the next thing tries to evaporate off. So simple distillation is for things that are pretty different in boiling point. So what happens, like we said, that substance that has the lowest boiling point will evaporate first, and evaporates up here, and then it's forced down into this condensing column. And so the vapor comes down here, and there are tubes hooked up to this tube right here that have water that flow just in a bubble around that middle condensing tube. It doesn't mix with the vapor. It's still separated from that vapor that's condensing in there, but it's there to cool that gas down so that it does turn back into a liquid. And then once it starts to drip out of here, it just goes down into your flask. Okay? Then we have a process called fractional distillation. And this picture, the second one down here, represents a small scale type of fractional distillation where this process is used for things that we're trying to separate that have boiling points that are close to each other. I mean, everything has its own unique boiling point, but some things have boiling points that are pretty near each other. And in order to get those separated using distillation, we have to have a process where, if things are evaporating, they have an opportunity to recondense before they get all the way to the top. And this just ensures that we get the best separation possible. So the only difference between simple distillation here and this setup is this extra tube right here. And there's little glass nodules on the inside of that tube. And as the liquid begins to evaporate and move up into that fractionating thing or column right here, it starts to touch those little glass nodules. And if its boiling point is not as high as the other substance, if it's accidentally evaporated a little bit into that tube, then it'll touch those glass nodules and then eventually just drop back down into the flask. And so this tube right here just ensures that we get a really good separation between things that have close boiling points. And the last, this is still fractional distillation. I just wanted to put this in here real quick because it's how the oil and gas industry separates the components of crude oil. So they have these big fractionating columns, and inside those columns there's these different levels, and they have the crude oil down at the bottom, and it gets heated up, and as the vapors begin to travel up this pipe or this tube, they start to cool down. The farther they get from the heat source, they cool down at each different level. And once they reach the point at which they're going to condense back into a liquid, they've cooled down sufficiently, they get collected at these different levels where they will condense at. All right, and then they get collected and pumped out somewhere else. So this is just a way for them to separate many, many components that are found in crude oil. And some of these components will be further broken down or separated or treated after they've been separated from the crude oil. All right, the next thing that we're going to talk about is chromatography. And there's lots of different types of chromatography, and even within the main categories of chromatography, there's lots of different, subtypes of chromatography. I'm just going to keep my explanation as simple as possible. So the first one that we're going to talk about is paper chromatography, and this is usually these days just used to separate pigments to see, how many different pigments there might be in inks or something. And you may have even done chromatography or some form of chromatography before, either in a science class or maybe as an art project, where you put some little blots of ink on paper, and then you put that paper, the very bottom of it, in some water or some kind of solvent and watched the colors move up the page. So that's paper chromatography. And then there's thin layer chromatography, which is very similar to paper chromatography, only it utilizes little glass sheets, little thin glass slides almost, that have a coating of silicone or some other absorbent material where the samples can move up in a solvent. All right, and then we have column chromatography, and there's lots of different types of column chromatography. I'm just going to kind of speak to the size exclusion chromatography because it's the easiest one to understand when you're just starting out in chemistry. So we've got this column here, and it's like a big empty tube, and it's got a little stopper at the bottom. And inside this tube, it's filled with some kind of medium, and it's usually some kind of silica gel or something that has the ability for a solution to move through it, but at varying speeds. So like if we're doing size exclusion chromatography here, then different size molecules will move through that medium at different rates. So maybe the smaller ones will move through that faster, and the larger molecules will take a longer time to move through. So you can see how as time passes, we're getting some separation there between those three sizes of molecule. But this is really good for things that can't be distilled. So if you have a liquid sample that contains proteins that are heat sensitive, you don't want to distill that because you'll destroy all the proteins. But you can use this type of chromatography to separate mixtures of things that are heat sensitive, or liquids that are heat sensitive. All right, and then there's some other separation techniques you can use. You can evaporate a solvent and leave behind any dissolved solids that might have been in there. You could use extraction, and this takes advantage of the fact that some things are soluble and some things are not. And even if some things are soluble or both soluble, maybe something is more soluble at one temperature than it is at another temperature. And let's say an example of this would be if I had a mixture of sand and salt, table salt. I mixed them together and I needed to figure out how to separate those. What I could do is I could think to myself, well, I know salt will dissolve in water, but sand won't. So if I poured water in there and I dissolve all of the salt, then maybe I can filter that and get the sand out, and then rinse that sand with some fresh water to get all this as much of the salt down into that liquid as I could. And then maybe I could evaporate all that water and leave behind the salt in the dish. So that's extraction. Crystallization utilizes the fact that some crystal substances, if we've got some crystal substance that's got an impurity in it, then we can dissolve it in an appropriate solvent and recrystallize that. We can force it to recrystallize, and when those crystals form, hopefully they're forming without the impurities. Maybe we can filter out some of those impurities before we recrystallize that. And then there's centrifugation. So this is where we're using a centrifuge. This device right here, you put things in these little test tubes and it spins really fast and it separates things based on their density. This is used when people are donating plasma. So if they're trying to collect plasma from you, they'll put your blood in these little vials and spin it, and you'll see a very clear separation where you've got the white plasma and then your red blood cells in the rest of the tube. You could filter or strain something. So this person right here is pouring this green solution into this filter and hopefully collecting something that's in that green solution. Sedimentation and decanting. So if you have a suspension that you want to let the particles settle to the bottom and then you can pour the liquid off the top, kind of like what's happening here. When we pour that liquid off of the top of a more dense substance, then that's also called decanting. So sedimentation and decanting can kind of work together. If you have the means, if it's not too difficult, you could physically sort things. You could take advantage of changes in the state of matter. So you can look at differences in boiling point, which we've already did when we looked at distillation. But you could look at other differences and see if maybe there's something you could take advantage of there in order to use to separate a mixture. And then there's, whether buoyancy, which is whether something floats or not, or magnetism, because some things are magnetic. If I had a mixture of sand and iron filings and I wanted to get all my iron filings out, I could use a strong magnet on the outside of a container to kind of collect those iron filings and get them out of that sand. So these are just all, a bunch of different techniques you can use. There's many, many more than what I've listed here. But basically anything you can think of that would take advantage of the differences in physical properties will help you separate the components of a mixture. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.